Okay, welcome. Before we start, I would like to show my respect and acknowledge the Bedegal people who are the traditional custodians of the land on which this meeting takes place, and to their elders past and present. My name is Henk. I'm the person of many kind of roles, as you can see here. I'm also the course convener for Code 3100, where the students are in here today. But I'm mainly here to announce the Arch Menu talk series, so welcome to everyone in the audience here at UNSW and abroad. The Arch Menu talk series is a series that we started as part of the ARC Center for Next Gen Architecture Manufacturing, where we invited guests to talk about topics and issues in computational design, digital transformation, sustainability, and so on, in various disciplines ranging from architecture to computer science to business. The talk today is the talk number 12. The title of the talk is Intelligent Tectonics, Performance-Driven Integration of Digital Design and Fabrication in Freeform Architecture, with our speaker today, Dr. Nick Bau from RMIT. A few words about Arch Menu before we hand over to Nick. Arch Menu is an umbrella organization that sits on level 4 here in the Red Center, that is looking into 4 different things. We are funded by the ARC, with the ARC Training Center for Next Gen Architecture Manufacturing. Several of the PhD students and postdocs around present today. We also got the CRCP funding for 3D printing houses in remote environments using local material. Again, staff and colleagues are here there. And we have a little architecture bureau, architecture computing bureau, where we design prototypes and build buildings from a smaller scale to a bigger scale, ranging from bioshelter and artificial reef to installations that we do in our office. And then largely Arch Menu Code, where we write software tools for the AEC industry as well. So in the context of the Arch Menu talk series, it is important to acknowledge and recognize that as part of our training, we have a mandate to develop 156 CPD courses, lifelong learning initiatives. So this one is a double effect. It's a lecture to the student, but it also functions as a CPD course for professional development, for colleagues that are in practice already and would like to know more about computational tools and processes that we offer. If you would like to know more about Arch Menu, we are quite present in the LinkedIn on our homepage, so feel free to visit us there. For all the students in the room, this is designed to put the telephone up and scan the QR code to register your attention. Not attention, detention. Attendance, exactly. Detention comes later. All right, why are you going to do that? I want to introduce to you Nick Bau. Nick Bau is a senior lecturer in architecture and PhD supervisor at RMIT School of Architecture and Urban Design, the same school I've done my PhD in, where he leads a Form X research lab. His expertise spans architectural technology, computational design, robotic fabrication, and intelligent construction. Nick is a senior member of the RMIT Center for Innovative Structures and Materials and a member of RMIT Post-Carbon Center. With over 60 publications, including high-impact journals, book chapters, and proceedings, he has also led several projects funded by the ARC Research Council and industry partners. His work has been exhibited globally, including Melbourne Design Week and Venice Biennale. Nick is an ARBV registered architect in Australia and an RIBA chartered architect in the UK. So you can use your own practice lecture about a CPD course to keep your registration going. He's also director of BB Architects, a partner of Amoeba Technology, the secretary of Cadrea, thank you for your services there, a member of the Digital Futures Organizing Committee, and an editorial board member of Artificial Intelligence and Sustainable Structures Journal. So with no further ado, Nick, thank you very much for coming to us today here at RMIT, not RMIT, at UNSW, and welcome, and thank you for your presentation.
Okay, yeah, thanks Hank for the invitation, and yeah, I'm very glad to be here to present my research at UNSW. So I just skip myself introduction, which is have been introduced by Hank. Yeah, so the right side is my practice and projects, and the left side my quick bio. So yeah, I just quickly introduce my background, which is I think is also quite interesting to everyone, which is from the study architecture, moved to the digital design, doing practice, then back to the academic. So I start my
Well, we can see you on Teams. I don't know what's happened there.
If you share the big screen, not this one.
Yeah, so I started my study architecture from 2009 and in MIT School of Architecture, and then moved to Melbourne for my master's study. And also about the urban design and the exchange to the CAHK and also the UPC Barcelona for exchange. After that, after graduate, I started the practical in the different companies, mostly in Australia, Melbourne, which is Cox, FKA, Noel Robinson, Basemar, Architects. So did a lot of the projects, high-rise building, children's hospital. Also part-time teaching at Monash University and Melbourne Uni about digital design, fabrication, construction technology. So I decided to leave industry from 2018, start my PhD when I was 29 years old, so it's never too late to start a PhD. So I started my PhD in School of Engineering, also part of School of Architecture. So my PhD is related to structural engineering, multidisciplinary study. Also, I start my teaching as a lecturer from MIT as 2018 to 20, then becoming lecturer, then senior lecturer now. So the project and the research direction I'm working on is the performance driving generative design and advanced manufacture based on the topology optimization and multi-agent systems. So the whole project and the background is what I'm working on. Yeah, firstly, the research background is start from the inspiration from the nature phenomenon and also the collaboration between the architects and the engineers, and the lost connection between the complexity and efficiency simultaneously. And the last one is an imbalance between architecture aesthetics and structure performance. So, especially from the nature structures, and the second one is the collaboration between architects. So my associate supervisor, PhD associate supervisor, Roland Stokes, built a lot of interesting design for the NGV pavilion, but sometimes it's very hard to build. So that's why we introduced a new algorithm and design tools to realize it, which is also creating a lot of negotiation between the designers and the structural engineers. And also the lost connection between complexity and efficiency. Yeah, most of people know this is Beijing National Stadium bird's nest, using a lot of the steel materials to creating the complex forms, which is to creating the form of the bird nest. Actually, they have very less structural optimization, and also the material is not efficiency, also for the long-term design construction process. And the last one is the aesthetics and the structural performance. So the structure here have a lot of columns, which is good, but a lack of the ornamental beauty. So my research arm is to creating the algorithm for the functional intricate forms. And another thing is to mass customization manufacture of the construction industry. So a few questions will be addressed for the collaboration, aesthetics, performance, advance, and how to fabricate them. So this is a diagram from the theory to the method and the application through whole my PhD study. So start from the theory. I combine with the two different algorithms, all the rules-based design approach, swarm intelligence, and the topology optimization, which is called BESO method, to integrate these two methods for the digital design. And to realize them, develop two methods. One is the swarm BESO method, another one is agent body method. To use these two methods to realize some intricate designs. Then use the robotic for the application. Robotic fabrication, additive manufacturers, so creating some prototypes to testing our design method and also the fabrication method. So start from this precedent, like Gaudi's building, Gaudi's church, and the Gothic buildings. And then nowadays, the smart slab by ETH and the pavilion by the ICD Stuttgart. And we are always balance the architecture and the structure, and to balance the aesthetics and performance. So we're thinking about the form from nature, especially for the generate nature forms rationally. So this is the animation from my engineering supervisor, Professor Mike Shear. He creating this yellow box and hanging on from the ceiling. And because of the gravity, so the shape become apple shape. So that's why he proposed an algorithm called BESO method for the topology optimization. So we use this method to do the modification, and also use this method to creating a lot of interesting components, structures, building forms. So this is basic background of the topology optimization. And topology optimization always use some small scale project like MIT Node, Arup Node, the jaw, and the chair. And use quickly can use the additive manufacturing to realize them. And later, a lot of Japanese architects and also Zaha Hadid, they use, and ETH use the topology optimization to realize the building components, building forms. Some project by this Japanese architects to creating the Counter National Convention Center, also the Shanghai Himalaya Center, interior design. So that's why we developed our software called Amoeba, which can use for the topology optimization, which is the plugin in the Rhino Grasshopper. So this is the basic knowledge of the topology optimization and our digital tools. For the fabrication side, I know many people know the robotics, and to use the robotic to replace the labor. And there's a robotics to layer in the bricks to help or increase the labors using robots. So this is the picture is showing the first machine to layering the bricks in the Western Australia. So at MIT, we also have a robotic lab, which have 4 robots. Mostly we're doing the large-scale 3D printing for the intelligent construction manufacturing. And I use them to use the clay concrete print, polymer print, and metal wire printing. So I will introduce the different projects which integrate with this digital design method and construction method. So the XFORM 1.0, which is 6 years ago, a project we did in Shanghai. And we developed our BESO method, which is oriental for the architecture design. Because we change different the data, try to make a diverse result for the topology optimizations. So you can see if we enter the same loading, same loading and same boundary conditions can creating the different results. So which is have more diverse for the designer for use. So the first one is we creating a column. So the column is very similar with the tree branch, and also the similar with the Gaudi's column in the church. So this is the full column models. So this is the design optimization progress. from a messy model to the optimized model for the smooth model. So firstly, for a small-scale testing. So small-scale testing using the small 3D printers. So the left side is a small 3D printer, and the right side is the robotic 3D printing. It's the first time we're trying to print start-stop, trying to creating the tree-branch forms. So each column takes 10 hours for printing. We just send over around 9 o'clock, then we pick up the column in the morning, which is about 2 meters high. So we print the 4 columns, then bring this and do some polishing. There's a lot of stream between the different branches, and design the up and the up joint and the base joint, and bring to the Digital Future 2018 and 19. So working with our students, and a few students from the Hanks course also joining us as well, to assemble this pavilion, so which has been done before COVID. Later, we developed a more complex geometry called X-Form 2.0. So the similar idea, we just cut it into 4 pieces, which is symmetrical forms, and add the supporting underneath, and the loading on the top. This time is 3 different heights of the curved roofs. This time, the topological optimization makes this column and the branch save 52% of materials. So the left side is a quarter of models, the right side is the full model of the prototypes, which is 4 meters high. So we're always being questioned by this complex geometries, maybe have better, have a worse structural performance. We do some FEA testing to prove this structure have a meet with the actual structural requirements, have very less movement, and then later compare with 1.0 and 2.0, so you can find the 1.0 only have a flat top, but 2.0 have 3 different height of the curved tops. So again, look at the top views and 3D printing a small one and make big prototypes. So we use the robotic to do the 3D printing and bring it to the Barcelona ISS conference to build up the prototypes. Unfortunately, we just bring our luggage, so we can only bring a quarter of the model for the fabrication for a lightweight structure exhibition. So this is 2 examples from the topology optimization methods. Then another one is multi-agent algorithms. The first project is the cloud effect, which is using the multi-agent swarm intelligence to generate the forms. So my contribution to the project is to add the structural performance in the swarm, in the multi-agents, to testing these complex carbon fiber structures. So the first iteration, you can see a lot of red materials because of the carbon fiber structure have a lot of deformation. So after a few iterations, integrate with my algorithm, it can reduce the movement, reduce the deformation to the 66 views. Then again, we print the external forms